All right, I hope the recording has started right now. So for today's lesson, we will be analyzing the following problem, which I will now read. A rod of length L and negligible mass is attached to a uniform disk of mass M and radius R, see figure below. A string is wrapped around the disk and you pull on the string with a constant force F. Two small balls, each of mass M, slide along the rod with negligible friction. The apparatus starts from rest with the center of the disk has moved a distance d, a length of string s has come off the disk, and the balls have collided with the ends of the rod and stuck there. The apparatus slides on a nearly frictionless table. Here is a view from above. So at first right here, you can see that it is in its initial position. No string has been pulled yet. Here in the second part, it is in the final position. The length of string S has been pulled off of it, and the balls have collided with the ends. So the first thing that it wants us to figure out is, what is the speed v at the center of the disk? This is part A. And for this part, we're going to be analyzing something called the center of mass velocity. We're just going to be treating this thing as being just like a point mass, a point system. We're not going to be thinking about like any internal structure of the system. So let's see, I need to first, how do I operate Zoom? How do I operate? Okay, new share. All right, there's my whiteboard. So the first physical principle that we're going to be thinking about here is going to be the work kinetic energy principle. If you exert a certain amount of work on a system, then you are going to boost that system's kinetic energy by the amount of work that you're doing. So we can write delta W, or let's see, there. W equals change in kinetic energy. Now, the definition of work is technically going to be something like this. We're going to have integral of the total amount of force times the distance that it's moved in some small amount of time. Now, the force on this thing is going to be constant as of now. So we can simply write F times D, where D, I would like to stress here, is the distance that the center of mass has moved. We're not going to be thinking about any amount of string that has come off. Again, we're just thinking of this as a point mass. Now, the kinetic energy of a system is going to be 1/2 m total times the center of mass squared. I will go to a new slide here. Change in kinetic energy equals 1/2 m total the center of mass squared equals force times distance that the center of mass has moved. In fact, I should probably just denote that like that. All right. So in our system, we had a disk here. And then we had these two little balls. I'll denote the mass of the disk by capital M and the mass of each ball by little m. So this means that the total mass of the system, m total, is going to be m plus 2m. New slide. So that means we have 1/2 m plus 2m v center of mass squared equals force times distance that the center of mass has moved. And then we can basically just do some very simple algebra here. We take 2 times force times distance over the total mass, which was m plus 2m. And then to solve for the velocity, we would then just take the square root of this. If it would help all of you, I can go back to the previous slide here. So you just take both sides, multiply it by 2, divide by capital M plus 2m, and then take the square root, as we have done here. So this gets done part A of the question. Let's see, where do I find? There we go. Because what part A wanted was simply for the velocity of the center of mass. So now it is time to move on to part 2 of this thing. What part 2 wants us to find is what is the total change in internal energy if the angular speed of the disk is omega. In this case, we're going to be assuming that the balls are in their final position at the very ends of the rod. So right now we are going to be not just working on like a point system. We're not going to be considering everything as if it's at like the center of mass. We're going to be working on an actual system, which means that we're going to have to take into account the internal structure of this system. So as usual, we're going to be working on, or the physical principle that we're going to be using is going to be the kind of the same work kinetic energy principle. The change in kinetic energy of our system is going to be the work that we put into it. And there's 3 basic types of kinetic energy. The first type is going to be, I'll just write this down on the slides as well. First type is translational. And this is just like kind of an object moving on like a certain path. It's kind of what you would naturally think of when you first think about kinetic energy. 2 is rotational. Rotational kinetic energy is also as it sounds. If you have, like, say, a bicycle tire and it's rotating, then you're going to have rotational kinetic energy. If you just have something rotating on its own, it doesn't have to be moving in any particular direction, as with translational kinetic energy. And then number 3 would be vibrational. This is kind of like a spring that's just like kind of bouncing back and forth like this. We don't really have to think about this too much in this example, I don't think. So the total work that you put into the system, W, is going to be equal to the change in kinetic energy plus the internal energy. And the internal energy is just going to be things like thermal energy and stuff like that that doesn't really show up as being an obvious kinetic energy term. I suppose you can think of this as kind of being the vibrational kinetic energy of the molecules involved in our setup here, but that's not really relevant for this discussion. So, new slide. Or actually, I think I still have some room back on the previous slide. The total work is going to be thus equal to change in KE translational plus change in kinetic energy rotational plus our internal energy here. So our translational kinetic energy here is just going to be the kinetic energy from our point mass system. That's going to be F times D. And then our rotational, because this is basically just the velocity that like our center of mass is overall moving like in a straight direction ahead. And so that means that we would just use our change in kinetic energy from the previous example. Because a point mass, that we were using in part A would not have any rotational kinetic energy. And so in that case, our rotational kinetic energy would then be 1/2 times the inertia of our system times omega squared plus u. And so basically, like our translational kinetic energy was 1/2 mv squared, where v was just the translational motion, whereas the rotational kinetic energy is just going to be expressed as kind of a rotational analog of our translational kinetic energy. So you'd have 1/2 as usual times the inertia, which is kind of like a rotational mass, I guess you could say. And then you would then multiply it by the angular velocity squared. That is the amount of angle that the system rotates in a certain time squared. So as before, we had FD plus 1/2 times the total inertia, angular inertia, I should say, times the angular velocity squared plus our internal energy. And so basically, we have two sort of things to worry about when we're thinking about our total inertia. We have the inertia of the disk and the angular inertia of the two little masses at the ends. So the angular inertia of just a disk, we can write this as I disk equals 1/2 times the mass of the disk times r squared. And then the angular inertia, you can write this as I of our two little masses would then just be m times r squared. This is going to be the angular inertia of each mass. Though I should clarify something here. So I'll use the variable r right here just to kind of express the distance from like some certain center of rotation. In this case, the total length of our rod is going to be L/2. I'll pull this up again. So the total length of this rod is going to be L. The distance from each mass from the center of motion is going to be L/2. And so the angular inertia of each ball is then going to be the mass of each ball times L/2 squared. Equals m times L/2 squared. And then this r right here is then just going to be the radius of our disk. I think I mentioned that before. And so we basically have right now everything that we need to solve this problem and give everything in the least number of terms. So we have work equals FD plus I total, sorry for my bad handwriting here, omega squared over 2 plus u. And then this is equal to force times distance plus 1/2 times 1/2 mr squared plus little m L/2 squared omega squared plus u. So this first term in the parentheses here, this is the angular inertia of the disk itself. The second term here is going to be the angular inertia of like each mass. And we have two masses here, so that's why we multiply it by 2. And then this is just going to be 1/2 times, so like if you like add these two together, you get the total angular inertia. And then you just take 1/2 times I total omega squared plus u. So we have work equals force times distance plus, let's see, 1/4 mr squared plus ml squared over 4 plus u. The 1/4 here came from just 1/2 times 1/2. That gives you 1/4. And then we have 1/2 times 2, that cancels out, but then you have the L over 2 squared here. So that gives you 1/4 as well. And so we have a very nice looking little expression here. I should probably actually do math properly and multiply by omega squared on the end here. Where's my eraser? Omega squared plus u. So now the question now becomes, what is the total work that has been done on this system? So in part A, we simply took the force times the distance at the center of mass moved. And then that gave us our translational kinetic energy, which is basically this term right here. If we're going to be thinking about the total system, though, we need to be thinking about the total distance that force has been applied, which is not just going to be the distance that the center of mass has moved, but it's also going to be the distance that the string has been pulled out. So you take the force times the overall distance that it's been applied, which is going to be the distance that the center of mass has moved, plus the distance that the string has unwound. And so this is then F, that's our total force, times D plus S. I can pull up the diagram again here if that would be helpful for all of you. Here we go. So yes, the total work done on the system would then be F times D plus S. Let's see if I can get back to my whiteboard here. And so you might be noticing that we can just simply cancel out the F times D on both sides. And then we're just simply left with F times S is equal to kind of this second line right here. And then in that case, we would just need to take Fs, F times S, and then subtract off all of this nonsense right here to get our internal energy. So we would then have F times S equals, let me go back to my first page here, equals mr squared plus little m L squared over 4 omega squared plus u. And so then this means that Fs minus 1/4 mr squared plus ml squared omega squared equals our internal energy u. So now we have our final answer for part B. I'll pull up the original question again so you all can see that. And so if you were doing this as an actual homework problem, you would then just simply take that answer and then symbolically shove it into that little box right there. And then you would hopefully be done with that. So this recitation / homework illustrates the importance of being able to work with both center of mass velocities and just treating everything as kind of being a point system, along with the conservation of energy and being able to work with extended systems. I will share the whiteboard again. Are there any questions? We can go back through all these slides maybe one more time. So for those who need to take notes, I can just simply page through these kind of real fast. So this was just kind of our center of mass velocity back when we were trying to figure that out. This is kind of the same thing on the previous slide. This was our final expression for the center of mass velocity back when we were just treating everything as being a point system. our three types of kinetic energy, the work energy principle for both translational and rotational kinetic energy. This was basically everything just kind of expanded. These were our angular inertia formulas. This was basically our work energy principle with everything substituted into it. And then here we worked out the expression for the total work. And then we basically subtracted some stuff from both sides, simplified, and then got the internal energy. So with that, our meeting is done if there are no further questions. And I wish you all a very good afternoon.